To move this lawnmower, I need to apply a force to it, but it's also important to note that that force is also applied back to myself. I can show this by trying to push the lawnmower without bracing myself, like standing on one foot. You may know of this as Newton's third law of motion, where each action has an equal and opposite reaction. By applying Newton's second law of motion, where force equals mass times acceleration, we can work out the relative acceleration of each object. If we ignore all the frictional forces, like the frictional force between the wheels of the lawnmower and the ground, if the mass of the lawnmower was the same as the mass of myself, we'd both accelerate at the same rate in opposite directions. As soon as my hands leave the handlebar of the lawnmower, the force between us ends, and so does the acceleration in either direction. But we'll both have an end velocity travelling in either direction. And we can actually work out the relative velocity between us by using the law of conservation of momentum. We calculate momentum by multiplying an object's mass by its velocity, and by applying conservation of momentum to this example, we can say that the end momentum of the lawnmower is equal to the end momentum of myself. Now, I know the mass of myself, so I can actually calculate the velocity that I'll be pushed back by, depending on whether I use a really heavy object, like this lawnmower, travelling very slowly, or a very light object travelling very quickly, like shooting a bullet from a gun. This law of conservation of momentum can also be applied to rotating objects, such as this wheel. Now, this wheel has a very low mass in comparison to myself, so I would need to rotate it to a very high velocity in order to give it enough momentum, in this case angular momentum, because it's rotating, in order to give myself enough momentum to rotate in the opposite direction. However, it should be enough to at least make me lose balance. Okay, that example was quite terrible, so I think I need to go and build a test rig to try and explain this a bit better. Now, reaction wheels work in exactly the same way as that bicycle wheel did. However, as I mentioned, because the mass of the bicycle wheel was very, very low and the mass of my body weight is much higher, I would need to accelerate the wheel very, very quickly in order to move my body weight in the opposite direction. So I've made a small test rig here to try and give a better example of how reaction wheels work. Here you can see a heavy aluminium disc which is mounted to the shaft of an electric motor, which is mounted to the backside of this blue plate. Now, this blue plate and the whole assembly here is mounted to a pivot which is balanced about to simulate a satellite in space or a drone in mid-air. It doesn't want to swing back to be self-level in its current state. Now, if I apply voltage to this electric motor, it will cause this wheel to spin in whatever direction the motor was wired up for. And this will increase the angular momentum of this wheel. And because angular momentum has to be conserved, it will also apply angular momentum to this blue plate. So, for example, if the disc were to spin clockwise, the blue disc would spin in the opposite direction, counterclockwise. Now, I haven't just wired this straight up to a battery with a switch. Instead, I've put some gyros and accelerometers on the back side of this plate, which should cause the plate to try and self-level itself, with this white pad being the top of the plate. So if I were to put it at an angle like this, it should try and spin the wheel in a certain direction to bring this foam pad up to the top again. So let's plug it in and see if this test rig works. Right, it's plugged in and I put it at a certain angle, so it should be able to correct itself. And there we go, it's brought the white pad up to level. Now, the wheel has become stationary now because it doesn't need to impart any more angular momentum onto this blue pad because it's where it wants to be. Now, what's also interesting about this test rig is that if I apply an external force to this blue plate, the gyros and accelerometers will detect that and therefore spin the wheel in the direction that I pushed to try and absorb all of the angular momentum. Let's give this a go. You see that? It spins the motor in a certain direction to try and absorb the rotation of this blue plate. Now, what's important to know about reaction wheels is that they can become what's called saturated, which basically the motor won't spin any quicker and therefore it can't accelerate the wheel any more than its current RPM. And this is a big issue with satellites, and I think it might be an issue with this drone. If I bring it back to level, the motor should stop. So I now have two wheels. This was the reaction wheel which was mounted onto the experimental test rig, and this wheel will be mounted onto the drone. Now this first wheel weighs 194 grams and this one weighs 85 grams. So it's less than half the weight of this first wheel. Now going back to the equation for linear momentum, which I mentioned at the start of this video, where mass times velocity equals momentum, it would suggest that this wheel would have a far greater momentum than this wheel if they're both rotated at the same velocity. But I think we need to take a look at the equation for angular momentum instead. This is the equation for angular momentum. Instead of being mass times velocity, it's in fact moment of inertia times angular velocity, which is the rate that it spins at. But the important part is the moment of inertia. If we apply conservation of momentum to this, we can say that the inertia of the drone times the rotational rate of the drone is equal to the inertia of the wheel times the rotational rate of the wheel. Now basically what we want to do is maximise the rotational rate of the drone so that we have full attitude control of the drone. And the way that we can do this is either decrease the inertia of the drone or increase the angular momentum of the wheel by either increasing the inertia of the wheel or the angular velocity. Now we can't increase the angular velocity any more than the electric motor is rated for, because it will only spin up to a maximum RPM. So basically what we're working with is the inertia of the wheel and the drone. So to have this as high as possible, we need to have a really high inertia wheel and a really low inertia drone. So let's talk about the inertia of the wheel. To calculate moment of inertia of either a disc or a ring, these are the following equations. As you can see, for a solid disc, like this first reaction wheel, the equation is half mr squared, which is half times its mass times its radius squared. Whereas for a ring, which is similar to this, obviously minusing the spokes in the middle, we can see that the moment of inertia is mass times its radius squared. So for these two objects, if they were the same mass and the same radius, then the ring would have double the amount of moment of inertia as the disc. So basically what this means is that the radius has a larger effect on the moment of inertia than the mass does, because it's squared. So if you were to double the radius, it's equivalent to timesing it by 4. Whereas if you were to double the mass, it's just the same as timesing it by 2. So this solid disc, although it weighs, weighs over double the amount of this disc, they actually have equal amounts of inertia. Now because this is slightly more complex shape than just a simple ring, what I did is I designed these two discs in my CAD program, and if I look at the calculations in the CAD program, I can prove that they both have the same amount of inertia. So what does this mean in terms of this project? Well, here I have two reaction wheels, both have the same moment of inertia, and when attached to the same electric motor will have the same angular velocity. This means they'll both be able to impart the same angular momentum onto the drone. But this wheel weighs half as much as this wheel, which will not only reduce the overall weight of the drone, because this obviously weighs a lot less and will hopefully increase the flight time of the drone, it also allows the drone to run much smaller motors in order to lift this wheel rather than this wheel, which will therefore decrease the inertia of the drone, which also assists to increase the angular velocity of the drone. So not only have we kept the inertia the same, we've managed to decrease the inertia of the drone, which is, as I mentioned before, is very important for increasing the angular velocity and therefore keeping the drone under control. So I think it's time to get building with this drone. Before I complete the build of this reaction wheel drone, I want to run through a few of the components that I've chosen to use to control the reaction wheels. Here you can see two brushed motors mounted perpendicular to each other, 90 degrees, and on the output shafts of these motors will be mounted the reaction wheels. Now these will be able to control the roll and pitch axis, and I won't be having a wheel for the yaw axis because I'm going to do that through aerodynamic control of the propellers. Now I've chosen to go for brushed motors over more modern brushless motors because it's very difficult to control a brushless motor at very slow revolutions per minute. They either need some kind of encoder or Hall effect sensor to know the exact position of the rotor. It's also very difficult to change direction of a brushless motor smoothly. Although drone speed controllers can change the direction of a brushless motor, it usually does a very hard braking manoeuvre and a very hard acceleration manoeuvre when changing direction. And I reckon this will cause issues with the reaction wheel when the drone is in mid-air. With a brushed motor, you can simply change the direction of the voltage and current, and it will just decelerate the motor and accelerate it smoothly in the other direction. The other reason is that these motors have a gearbox, which means the reaction wheel can receive a lot of torque from the motor without spinning too quickly and causing any kind of gyroscopic issues. To drive these brushed motors, I have a motor driver down in the bottom of here. The motor driver can drive both motors, which is quite handy, and it's controlled via this Arduino Nano. Now in order for this Arduino Nano to know which way to spin the motors to control the drone, I have a flight controller from a regular drone, which I've programmed to output servo controls which can be read by the Arduino Nano. Now this flight controller has gyros and accelerometers in it so that it will be able to detect any movement of the drone, and I can also control the movement of the drone by using a receiver and a radio control. So if I plug in a battery, we should be able to see everything light up, and it should arm in a second. There we go, so that means the motors are all ready to spin, and if I tilt the drone it should spin up one of the motors. If I tilt it in this direction, it should spin up this motor. So yeah, so that motor spins, and if I tilt it this way, the other motor spins. Now I can also put my radio control here and control the direction using my sticks, which means I can control the drone in mid-air. So now I know that the gyros and accelerometers are working with the Arduino to control the reaction wheel motors, I think it's time to solder up the motors to lift this thing into the air. Now you might be wondering, Tom, why are you trying to control a drone using reaction wheels? Drones fly perfectly fine as they are. Quite honestly, I have no idea. Well, I find the physics behind the reaction wheel quite interesting, with the whole conservation of momentum thing. And if this drone doesn't fly, it's only going to be a big waste of time and money. And even if this drone doesn't fly, at least I've learned something and hopefully taught you something. I still really hope this thing does fly though. Right, so I know that this still looks more like a Christmas decoration than it does a drone, so I've hung it from the ceiling to try and tune some of the parameters inside of the flight controller. By hanging it from the ceiling, I basically free up one of the axes. In this case, it's the roll axis reaction wheel, and I can actually simulate what would happen if I apply an external force to it, where the reaction wheel responds. Not only that, but I can also take control with my radio control and make it spin. See, I can do pretty accurate 360s, 90-degree increments. So I have pretty good control over that axis. So the reaction wheel drone is now complete, and hopefully it looks slightly more like a drone than it used to, with the propellers on the top and the bottom. In terms of the controls for this drone, the reaction wheels will control the pitch axis and the roll axis. To control the yaw axis, I'll be using differential thrust of these propellers. The propellers are counter-rotating to prevent any torque rotation during a hover, and then to control the yaw axis, one will speed up and one will slow down, and then the differential in torque will hopefully twist the drone in midair. So basically this whole thing is controlled by changing the torque of an object like a propeller or a reaction wheel. So I'm going to charge up the battery, and then I think we're ready for a test flight. I put the drone on a paving slab to not only keep the propeller from hitting the grass, but also to make sure that it was perfectly level. If it wasn't quite level, the reaction wheels would try to make it level and may become saturated even before it takes off. Let's try that again. And again. Ouch. Time for some repairs. So I've made a few modifications aside from just swapping out the old broken propellers. For some reason the pitch reaction wheel has far less torque than the roll reaction wheel, which is really weird because I bought them from the same supplier and they're the same rated motors, both rated for the same RPM and also the same gear ratio. But for some reason this one has a lot more resistance or torque than this one does. I'm not sure whether it has a different gear ratio or different magnets, but what I've done is adjusted the settings inside the flight controller to basically rotate this wheel faster than it was doing before. I've also changed the battery for a higher voltage battery, which will be able to give the motors more power and also a higher end RPM, which should try and delay the saturation of the reaction wheels a little bit longer. To balance out this battery, I've added some lead weights to this leg here. And my plan for the next flight, I haven't got that many propellers left, but my plan for the next flight is just to try and get it off the ground as quick as possible, and then see if the reaction wheels can take control. I think if I spend too much time on the ground, the reaction wheels try and fight the ground to try and roll it and pitch it, and it just sort of ends up saturating them before it even takes off. So let's take it out for another test flight. The next few attempts didn't seem to be much better. But then I took a look at the slow-mo of this flight and realised the drone was rotating about its yaw axis. So I increased the yaw PID values and tried again. The yaw axis seems to be holding now, and I think we could be close to success. Or maybe not. But then this happened. The slow-mo clearly shows the reaction wheels trying to hold the drone's orientation, and they aren't spinning anywhere near fast enough for maximum RPM saturation to be an issue. As successful as this 8-second flight was, the following flight took a pretty hard dive, resulting in a broken top motor mount. So, with the death of this propeller-powered reaction wheel CubeSat drone looming over the horizon, it was time for one last test flight. So it's time to wrap up this project. It's been quite a long project and also quite a long video. It finally ended in destruction of this top motor mount, and that last crash also managed to take both reaction wheels off of the motor shafts. There's a few cracks in these legs, and I think the frame actually cracked around the side here as well. So it definitely needs some repairs done if I want to try it again. As I mentioned earlier in the video, I'm using brushed motors to control the reaction wheels. And the way that I'm controlling the torque output to the wheels is by varying the current supplied to the motor. Now the problem with this is that the torque output is not always relative to the current input. In fact, when the reaction wheels are spinning slowly, they can output a really high amount of torque from the motors. But when the motors are spinning quickly, like if it's already at a certain angle and it needs to recover, the torque reduces a lot when the wheel is at high RPM. So the actual torque output is not linear, and this is very difficult when you're trying to tune the parameters in the flight controller, because a flight controller just thinks, oh, I need to apply a force in this direction to get it up to this direction. And you have to preset it of how much force it needs to apply, but when the output force isn't constant, it's very difficult to counteract for that, basically. There is a way around this. Some brushed motors come with encoders, and I think this is the only way forward with this. So basically, I'll program the Arduino to measure the revolutions per minute of the motor, and then instead of just varying the torque of the motor through increasing the current, I can basically work out the acceleration of the motor and then apply the necessary current to try and match that acceleration. So instead of having the acceleration of the wheel controlled by just the current, it's actually measured and then controlled using a closed feedback loop. And I think this is the only way to get a constant change in momentum of the wheels. Right, I could keep going on about potential solutions and improvements, which I should have done on this project, but I'm going to end the video here. I'd like to thank you very much for watching. I would like to say thanks to 3D Prints Filament for sponsoring this episode, and a huge thanks to all of my Patreon supporters. You guys make these videos possible. One quick thing, I'm not going to be doing weekly videos, at least for the next month or two. I'm still working flat out on projects, but I've got some slightly bigger projects. I'm trying to get some more bike projects done as well. So I'm going to spend a bit more time focusing on longer video projects and upload them when they're ready to be uploaded, rather than trying to rush out part 1, part 2 videos. So bear with me if you're waiting for weekly videos. I apologise, I'm just going to put that on hold for the next month or two maybe. But yeah, if you enjoyed this video, then it would be grateful if you could leave a thumbs up. If you're new to my channel, please click subscribe down below. And if you enjoyed this video, it'd be great if you could share this with your friends if they're interested in any kind of reaction wheel satellites. If you play Kerbal Space Program, that's where my idea originally came from with this. So yeah, I could keep talking forever. Thanks once again for watching, and I'll see you in the next video. Goodbye.